Hi, this is Sarah Mitchell coming to you from NASA's Goddard Space Flight Center, and I have a very special Skype call today with some of the members of the SuperTIGER team who are calling me from Antarctica. Hi guys, welcome.
Hello.
Hi.
Hi.
Tell me a little bit about yourselves.
So my name is Jason Link. I am a scientist working at NASA Goddard. I am down here for the SuperTIGER flight. This is my third trip down. All of them have in fact been for the Tiger instrument starting in 2001. Nathan?
Hi, my name is Nathan Walsh. I am a graduate student at Washington University, and this is my first trip down to Antarctica to work on SuperTIGER, which I will be doing my thesis work using the data that we get from it.
Hello, I am Brian Rao. I'm a research assistant professor at Washington University. I've worked on Tiger since I was an undergrad. I worked on it as a graduate student, and I'm still on it. And this is my second time to Antarctica.
So where are you guys right now?
So we right now are in Prairie Lab, which is the main scientific laboratory at McMurdo Base in Antarctica. We are in fact in the staging area for where they take equipment out into the field.
Terrific. So what is SuperTIGER?
SuperTIGER is a large area ultra-heavy cosmic ray detector. It's a balloon-borne instrument meant to fly at stratospheric altitudes.
Okay. Why is it called SuperTIGER?
Well, SuperTIGER is a follow-on to the original Tiger experiment, which is an contrived acronym. Tiger stands for Trans-Iron Galactic Element Reporter. So what makes SuperTIGER super is that it is much larger than the original Tiger, approximately 4 times the active area. And so essentially it's a super-sized Tiger, so it's a SuperTIGER.
Well, so what does your SuperTIGER observe?
So as Brian mentioned, our SuperTIGER measures galactic cosmic rays, specifically ultra-heavy galactic cosmic rays.
What are cosmic rays and why are they interesting?
So cosmic rays are high-energy particles that originate outside the solar system, propagate through the galaxy, and some of them come here to Earth where we detect them. They're particularly interesting for a lot of reasons. One is they are one of 2 kinds of matter from outside the solar system that we can directly sample, the other being stellar dust. Another reason they're interesting is that these particles can be at incredibly high energies, much higher than any accelerators here on Earth can produce. So it's a way to study not only material from outside the solar system, but to look at very high energy particles and understand the building blocks of nature.
Wow. Well, so in particular, you're studying ultra-heavy cosmic rays. What can they tell us about cosmic rays in general and the universe?
So ultra-heavy cosmic rays are cosmic rays that are made up of elements with about 30 protons or more. And these elements are ones that are synthesized in extreme conditions like supernova or binary neutron star mergers. So if we can measure the ultra-heavy cosmic rays, it can tell us more about how cosmic rays are formed in these types of events and also how they're accelerated.
So you mentioned binary neutron star mergers, and just this past month there was a huge announcement of a neutron star merger that was observed both in light and gravitational waves. And this was a big deal because it was the first time that that was seen in both of those messengers. How does this relate to the research you're doing with SuperTIGER?
Well, as you said, LIGO measured the gravitational wave signal from that event, and that was the first time that's happened. And Fermi measured the same, or they were able to look at it afterwards and see the gamma ray signal coming from that same event. And so basically we're in an age where multi-messenger astronomy is possible, and cosmic rays that could come from that event offer a third, in addition to other messengers that we can use to look at these events.
Well, cosmic rays wouldn't come directly to us from that event because cosmic rays being charged are deflected by magnetic fields and they take a lot longer to get here and don't travel a direct path. But cosmic rays from similar events would give a signature that would be indicative of this kind of binary neutron star merger event.
And one of the interesting things that we're able to do is to look at what elements we detect here on Earth and propagate it back to the source, which is believed for many of the ultra heavies to be binary neutron star mergers. So we can actually quantify the amount of heavy material that might be produced, which is something that they can't quite yet do with the photon measurements that they're making.
Well, that's terrific, and it's wonderful to see all the messengers coming together in astronomy. So you mentioned that there have been other TIGER and SuperTIGER flights. How many flights have occurred before this one this year?
Well, there have been essentially 3 TIGER-like instruments. The first TIGER was more of a proof of concept. It flew once after 3 campaigns, and it demonstrated that the instrument configuration, the instrument design, was good to measure cosmic rays past iron into the UH range. And then there was TIGER LDB that Jason worked on as a graduate student, and I did analysis for and supported the second flight for as a graduate student. And as given the results, gave preliminary results in the UH range, and then that flew twice in 2001, 2003. And now SuperTIGER's flown once, and we're going for its second flight.
So what results do you hope to get from this flight, and what do you hope to learn that adds to what you got from the earlier TIGER flights?
The ultra heavy elements that we're measuring have not been measured or measured well by any other instrument. So we are truly making some of the first measurements of the individual element abundances, and these are very, very rare elements. So we need a large instrument with a very long exposure time in order to get 10, 15, 20 events, which is about the minimum we need to have good statistics to be able to do science.
And so what distinguishes TIGER and SuperTIGER from previous measurements is the ability to resolve individual elements without the confusion.
The elements you're measuring are the elements that we have here on Earth, so you're making direct connections between the things that we're made of and that our world around us is made of and these cosmic rays that you're catching?
Yes. In fact, people might be interested, but if you look at many of the materials we use day to day, gold, platinum, lead, that all came from these high energy astrophysical events in the heart of stars, and that is what we're in fact studying.
Awesome. So, changing gears a little bit, how does the SuperTIGER instrument work in layman's terms?
So the instrument is made up of layers of detectors, and there's 3 different types. And when a cosmic ray passes through the detector, it deposits energy in each layer, and that energy is in the form of light, and that's how we collect it using photomultiplier tubes, which essentially give us a signal telling us how bright the light was when it passed through the detector.
So when people talk about measuring cosmic rays, you're really not catching them, you're detecting them as they pass through your instrument.
Yes, yes.
In fact, if we see a sign that the cosmic ray has done more than just lose energy passing through, if it were to collide with the nucleus within the detector and interact, that's an event we really can't analyze. We require the event to pass through all the active parts of the detector without interacting for us to be able to analyze it.
So who built SuperTIGER? Where was it built?
Well, SuperTIGER is a collaboration of 4 institutions: Washington University in St. Louis, NASA Goddard Space Flight Center, Caltech, with Jet Propulsion Lab participation, so I guess that really makes us 5 institutions, and also the University of Minnesota. WashU and Goddard did most of the construction.
So it really takes a village.
Yes, and it should also be mentioned that Tiger is an evolution from the very first flight to where we are today. And after each flight, we have improved on the instrument and made everything better. So when you say who built it, this starts back with the folks who in the 90s built the first Tiger instrument, and it went through various iterations to where we are today.
So I think the big question would be, why does this have to go to Antarctica? Why can't you just fly this anywhere?
Well, there's a few reasons, I guess, but the main one is that this is the place we can fly the longest safely. Above Antarctica, during the summer here, a circumpolar vortex sets up, so the wind basically circulates around the pole, and our balloon typically follows that path and stays above Antarctica, so we can keep it up for as long as possible.
Another particularly important reason for flying in Antarctica, especially if you consider that we want to fly for a long time, like 55 days, is that we need power. And back in the old days when we started, we would fly with just batteries, but that works for maybe a day. So we rely on solar power, and fortunately in the summer here, the sun's up all the time. We might move up and down in the sky some, but it's up, and so we have power continuously.
The other important thing about flying when it is always daylight is when you have day-night cycling of the balloon, you will lose altitude in the balloon. And so here, without that day-night cycling, the gas is always at roughly the same temperature, so it makes it possible to be flying at the high altitudes for a long period of time.
And the reason why we don't want to change altitudes, because if you sink lower in the atmosphere, you have more atmosphere above you, and when a cosmic ray is going through the atmosphere, it has a higher chance of interacting with a particle in the atmosphere because it'll be passing through more of it. So the higher up we are, the less atmosphere we have to interfere with the cosmic rays that we're measuring.
And we're above all but about a half a percent of the atmosphere. And even with just that little tiny fraction of atmosphere, we lose a very significant fraction, like around 50% or more of the particles will interact just passing through the atmosphere.
So how high is that in the atmosphere with just that tiny bit above you?
About 130,000 feet is the goal that we try to reach, and it's usually, and it will all depend on the balloon and the atmospheric conditions, but usually it's between about 127 and 130,000 that will start off at.
And SuperTIGER had a wonderful balloon that endured very well. Jason's Tiger flight in 2001 had a leaky balloon.
Yes.
That spanned quite much greater range, but these are things you have no control of.
So you're talking balloons. Why a balloon? Why not just send this up into space?
So a balloon has a lot of advantages. The first is it is a lot less expensive to build and fly on a balloon than to build and fly on a rocket experiment. And so that allows us to design and build our instrument quicker, because we don't have the same expense in design, and we don't have to go through all of the tests that you do for a space mission. For instance, a space mission has issues of vibration, which we don't have on a balloon instrument. It's also something where you can have students be far more involved in the building of the instrument. A spacecraft is very technical and very complicated, and very often you will need a lot of specialized engineers and technicians, and it is much harder for students to be involved. As Nathan today was tightening cables and checking things out, and he wouldn't have that opportunity on a spacecraft. So there's a lot of good things about balloons that let us test and move quickly. The other big advantage for us on SuperTIGER is we have a very large instrument, which would be very difficult to launch into space given its mass and size. And we need the instrument size in order to measure the cosmic rays.
One advantage to flying on a balloon is that you can recover the instrument, right? So you get to fly it again and make improvements and work your way towards a space instrument, for instance. I mean, we started, Tiger wasn't the very first idea along these lines. The group actually worked on previous experiments, balloon-borne experiments of different types. So one can spend a lot of time doing development for an experiment that you might hope to one day put in space. You can do it iteratively with a balloon, try different things, see what works, see what doesn't. You can do that very cost effectively.
So what's your launch window? When does that open?
So the launch window depends on a couple of things coming together. The first being that we have checked out our instrument and it is ready to go. And our goal is to do that by the first week of December. We also need to have the polar vortex that Nathan mentioned set up. That is in the process of doing so, and the weatherman down here thinks that that will hopefully have set up the first week of December as well. The other thing that we need to have happen is we need to have a day where we have calm winds and clear skies to have a good launch. When that happens is anyone's guess with the weather down here in McMurdo. So the first week of December we hope, but a lot depends on the weather.
How big is the SuperTIGER team that's down in Antarctica with you right now?
There will be 9 people total deployed, 5 from Washington University and 4 from Goddard.
Well, so thank you for joining me, Brian and Nathan and Jason, and best of luck getting ready for launch, and we'll keep updating us.
We will.
All right.
Thank you.
Thank you.
Thank you.